Okay, we are now recording. We are in YouTube. I'm with problems with my camera, that's why I'm not appearing. So I just noticed like 5 minutes before getting, so I didn't have time to fix. But okay, the other thing is are working. I can share my screen and have the lecture as usual. So today I'm planning to talk a little bit about uh, nonlinear optics, and we have made some applications to quantum computing, like following the the Nielsen Schwenk book. So let me share my screen. Okay, hope you guys can see. Um, okay, so let's start. Like, you guys can see my slides, right?
Looks good.
Okay, so good. Just a problem with the camera, but the more important is the screen. It's working well. So again, today I'm talking a little bit about uh, nonlinear optics, just a brief introduction. I was like, before I started, I was like in doubt if I should make a bigger review about nonlinear optics like I did for coherent states. But I decided now just to make like a short introduction. If you guys feel necessary, please is too much short. I mean, if you guys are interested to see more details about nonlinear optics, so we could like to make another lecture to see with more details, like some specific things. So some things are just like show, not make demonstration, and I'll let do to make the most of the calculations for the part of the quantum part, not the classical. So okay. So, but in the end of the lecture, I ask you guys, oh, we would like to have more a complete review. I mean, see more details. I didn't understand well this part here, and we could do this in another opportunity. So in the next couple of lectures, I'm thinking like today and next Friday, we will discuss a little bit about nonlinear optic materials in the applications for quantum computing. And when we do that, we finish this part, like nonlinear, like optical photon quantum computing. Then we go to quantum electrodynamics cavity. That's the other application of photonic quantum computing. So another model of photonic quantum computing. So nonlinear optics, let's start, is the study of a phenomena that occur as a consequence of the modification of the optical properties of a material system by the presence of light. Typically, only laser light is sufficiently intense to modify the optical properties of a material system. Nonlinear optical phenomena are nonlinear in the sense that they may occur when the response of a material system to an optical field depends in a nonlinear manner on the strength of the optical field. And we see some examples soon. To describe more precisely what we mean by an optical nonlinearity, let us consider how the dipole moment per unit volume which is also known as the polarization given by the letter P, the cap P, of a material system depends on the strength E of applied field. So the applied, like in this case, electric field, right? E here represents the questions. Can I see?
Yeah, Carlos, I got a quick question. Not being a physicist, I wanted to ask you this. Um, I when you say optical field, when I think of fields, I think of like magnetic fields, gravitational field. What exactly is an optical field?
No, in this case, it's just like electric field.
Electric field, like an E and
Yeah,
M
we
line.
make like because my camera is not working, but I'm pointing here. But we make the electric field like to access a material, and this electric field will like let's say turn on the nonlinearities in the system.
Okay, thank you.
So, but I'll show here. So, yeah, optical field in this case is like it's the electric field, but because it's the electric field inside the optical material. That's why, in this sense, I don't know if it's a better, is a good option of words. So, okay. So, in the case of a linear optics, the induced polarization depends linearly on the electric field strength in a manner that can often be described in this way. So P can be described in terms of epsilon zero, which epsilon zero is the permittivity of the free space. And this letter here is chi, chi in the index one. I will always call like chi one, okay? Is the linear part, the linear susceptibility. And this is my field, like in this case, electric field. We also have magnetic susceptibilities, but in general, they are much smaller than the electric susceptibilities. So most of the case, when we are considering like materials, these susceptibilities here, the electric susceptibilities that I will call only susceptibility is the dominant term. So in this expression, when we are like in the graduate courses in the university, when we are in the studying classical electrodynamics, in general we see this, like we see Maxwell equations in a material, and we go until the linear part. So in general we study this in classical electrodynamics books. But when we are in the nonlinear optics part, in fact, this P, it could be written in terms of a power series in this way. Chi1 here is this part, the linear part, linear term, and these are the nonlinear terms. E square, chi2, and chi3 are the second and third order nonlinear optical susceptibilities. This expression is confirmed by experiments, but there is a way to show this expression using like first principles, using the theory. Then we can find an expression like that and evaluate who are the chi1, chi2, chi3, and so on. I'll not do this here, at least for now. If you guys want, we can like have a bigger review about this from where these terms comes. But today I'll just tell you, okay, this expression here is confirmed by experiments. This is true, but the materials. But you can prove this using like first principles, of first principles. In fact, I would show you guys, but because of the problem with my camera, I will show a book that you guys could see, a book about nonlinear optics, but I'll put in the reference when I'm writing in the whiteboard. I will write there because you guys can see because my camera. So okay, but this is not the real expression. This is a simplified version because we know that P and E are vectors and not scalars. I'm written like a scalar form. That in fact is for our purpose here in studying quantum computing, at least in the level of the Nielsen-Schwenk book, we consider these quantities as scalar. But we know that a P and E, in fact, are vectors. When we write like the, the expression in terms of vectors, here, just the notation, so Pi here is the vector in the direction I. So chi1, chi2, and chi3 are tensors. So chi1 is a second rank tensor, chi2 is a third rank tensor, chi3 is a fourth rank tensor, and so on. Okay? And one thing is in many materials, like this chi2 term here is zero or almost zero. When this happens, we are considering like materials that that are called like centrosymmetric materials. In general, like a brief explanation about the centrosymmetric materials is that when you have like opposite directions in this material, the opposite directions are equivalent to a inverse center. So you have a center, and when we consider like the opposite directions in the material, they are like equivalent. So when this happens, we call the material like a centrosymmetric material. In this term, chi2 is zero. That's the type of materials that we use in our example when we apply for quantum computing. If I'm not wrong, I think the silicon is a type of centrosymmetric material. Not totally sure, but it's just one example. So when in this case, centrosymmetric materials, the nonlinearities are turned on when we use like the chi3. So we'd have this first term, the linear term, plus the nonlinear term. And of course, if you are in the vacuum, not inside the material, the chi's are, all of them are zero, and the polarization is none. So we, as I told you, we will consider like the scalar form of P when we applied for quantum computation here. So in writing P in the scalar form, we have assumed that the polarization at a certain time t depends only on the instantaneous values of the electric field strength. So this assumption that the medium is the assumption is that the medium responds instantaneously will also imply that the medium must be lossless and dispersionless. So, like this type of things, of course, that are only approximation. All materials, for instance, they are dispersion. They have dispersion, are not dispersionless. But you can always, like, in certain wavelength, when we are like studying the the the, the susceptibilities, we can find some places, some bandwidth where the susceptibility tensors are almost constant. And when they are almost constant, so we are in this dispersionless regime. Okay. So in general, the nonlinear susceptibilities depend on the frequencies of the applied field. But under our present assumption of instantaneous response that this item here, we take them to be constant. So the chi, the susceptibilities that we consider here are constant. And these are possible experimentally. We always have like a certain bandwidth where we can consider, we measure the, the susceptibilities, and in this interval, you see that they are almost constant. Okay. But in general, if you consider like all bandwidth possibles, so the susceptibilities are not, the materials are not dispersion, and consequently, chi depends on the frequency, on the wavelength. So, okay, let's see this, some of these examples here. So I'll make some review very quick about an expression that the Nixon Shuang like start. It just gives the expression. So I'll try to make a brief calculation to find this expression. But again, if you guys wish to see with more details about the things classical nonlinear optics, so we could return in another Friday and see, and then return to quantum computation. Okay. So in general, the refractive index of main material can be described by the relation. Just to mention here, the book that I'm using to make this short review is this one. Let's see, reference. Nonlinear optics, third edition that I have here. And the author is Robert W. Poppy. Okay. So you can see it's a book only about nonlinear optics. So makes just a brief introduction here about the things that we need, at least at this point, to make the quantum computation. So the refractive index, I'll call n, is given n0 plus n2. I'll call here bar, just to make the difference that I will define another term here briefly. So in terms of electric field, E is square, nonlinear term. And this brackets here, it means average in time, okay? So I'll put this T here. This means that I'm averaging in time. So it's classical, it's not quantum. So far, everything is classical. This n0 is the refractive index, like with field refractive index, and this n2 bar is a new optical constant that sometimes called second order index of refraction. And in this, just to in this book here, what we are seeing today is just a short introduction of chapter 4. Okay, most parts are present in chapter 4. So this eta 2 here, it gives the rate at which the refractive index increases with increasing intensity, like optical intensity. We see details a little bit. Okay, but we know that the electric field or the electric field, we could represent it by, we could write like E, just for short, E of t as an amplitude, E omega minus E omega t plus complex conjugate, E omega I omega t. So we need E square, E tilde E square. So E tilde, this is tilde E square. It's just this product here. And so far everything is like classical. We could write this in this way. E square exponential minus 2 omega t plus E conjugate exponential 2 omega t. And we could average E in time. So average in square in time that we need in our expression. We are just like averaging a function. We can like choose the interval. Let's say if we average in an interval 0 pi over omega, just for to give a much simple expression, this would be like because I'm using, just remember, when I'm averaging a function, I forgot to put here. Let me remember. when I'm like averaging a function, let's say f of x in x, this is 1, b minus a in the interval a, b, the function dx. Okay? So, in this case, I'm averaging e in time, and I will choose the interval 0 to pi over omega, just to give a simple expression. So in the interval of 0 to pi over omega, this will be just pi over omega. The t in this expression here, e squared, in this case is this expression. 2e plus e squared exponential minus 2i omega t plus e conjugate square square exponential 2i omega t. Okay. Okay, in this integral are simple. Remember that this e here is a function of omega, so it can go outside the integral. Because it's just the amplitude part. This the time is here in this exponential. So when doing this pi over omega, doing this integral, this will give us only pi over omega, right? This term, because e can go outside the integral, will be integral of dt. So this is pi over omega. And this part here, when we will do this integral in this interval, we find that this is 0 and this is 0. Of course, we could like have choose another interval, but just give like a constant with some constants here, and it would be a more complicated expression that we don't need here because we just want to see like the. So this integral here is pi over 2, and that is this term here, times pi over omega. So this is 1. Okay? So this is not 1. This is 1 times this here, 2. Because this term go outside the integral. This is 0, this is 0, and this here, the integral is just pi over omega times this part that go outside. So it's 2 e squared. So this will be just e squared. So eta for n is n0 plus 2 n2 bar e omega squared. So okay, I call this equation for 1. Okay, so this change in the refractive index described by equation 1 is sometimes called the optical pair effect. Okay, so this is the famous Kerr effect that appears only in the linear part. And we see that this term here, this new index of refraction, is proportional to chi over 3. We see now. Yes, questions?
Yeah, Carlos, so you're saying that the refractive index of a material could change. Is that E, that energy field that's changing it, is that something internal to the material or is it related to the
No,
intensity?
no, you apply it. You apply the laser. Yeah,
So
you apply the laser. So if you turn off your laser, you will not see the effect. I
okay.
mean, it's
So
the laser that's activated. It's there, of course, but to activate it, to see the effect, you need to have a laser and get
you need to
into the.
apply it. And then
It must be like intense enough that because in general this term is very small, this N2. So it must be intense enough to compensate and you can see. Because N2 in general is much smaller than N0.
okay, and then optical, the change in refraction, then say you apply a laser to a material, it changes the refractive index of the material. If I would apply another light to that material, that light would experience that new refractive index.
Yes, yes, this is the idea. Yes, to have the
Thank you.
compensation. And then the photons could like interact and you could like make computation. I mean, in principle, this was done to another goals, but in our interest is exactly this you said. This the interaction of photons in the material will be possible because of this nonlinear effect. So okay, this interaction or the interaction of a beam of light with nonlinear optical medium can also be described in terms of the nonlinear polarization. The nonlinear polarization. Like the total polarization for centrosymmetric materials that we consider, the total polarization to centrosymmetric materials. And as I told you guys, the like opposite directions, just make a give the idea, like in opposite directions in the material, they are equivalent in relation with the center. So this would be equivalent to this, and this with this one, let's change the color. Just to a vague idea that what I mean by centrosymmetric material. So the colors are equivalent. So this with that, and so on. And the center is the the region that they are equivalent, the reference region. So the total polarization through centrosymmetric materials is described by, this is like just to give idea, okay? The centrosymmetric material. And this is described by this P, let's say P omega, scalar, okay? This is my polarization vector. So my polarization, my total polarization that I'm considering like scalar, because I'm in the limit where K can be considered constant. So chi1 E omega plus, because it's centrosymmetric, so chi2 is in general 0. So the first nonlinear term that appears will be this one. And again, these numbers here, by instance, 3 here, this is, you can show experimentally, but you can prove this using first principles. But I'm not doing this today, okay? But if you guys want, we could do. So this, when we can have like different frequencies. So I'm calling here omega prime. Omega. Okay. And you have other terms. So in general, we could like write this as epsilon 0, Q, I'll call Q effective, F E omega, where effect was defined as chi1 plus 3 chi3 e squared. So in order to relate the nonlinear susceptibility chi3 to the nonlinear effective index, and 2, we note that and again, this is like a phenomenological expression, but we could prove it if you see more details. Okay, they are related in this way. So I'll call this equation 2, this equation 3. So if I use equation 1 using equation 1 in the left-hand side of equation 3 and 2 and equation 2 using equation 1 in the left-hand side of equation 3 and equation 2 in the right-hand side. We just remember we found eta squared. Eta is n0 plus 2 n2 bar e omega squared because this is squared. So I'm using this which equation? I'm using this equation. Yeah. This red here. This is the same as 1 plus key effective. That's this term. Chi1 plus 3 chi3 e omega squared. So we could like expand the left-hand side. So expanding terms up to e squared, we would have eta 0 plus 4 eta 0 eta 2 e omega squared plus the other term. The other term will be to the 4 and eta 2 bar 3 square. But in general, this term is smaller than this. So if you square, will be much smaller. So this is this. Like 3 e omega squared. And then just compare the terms. So this, the term up to e squared is this, and the other term, this here, with this. There's 0 other term. So eta 0 e squared is 1 plus chi1 or square root. And the other term is 4 eta 0 eta 3 square equal 3 chi 3. So eta 2 is 3 chi 3 eta 0. And eta 0 in general is given in this way in the material. 1 plus chi1, the linear term. Okay. outside the material in the vacuum, it's 1, because chi1 will be 0. And these guys, chi1 and chi3, you could like measure in the lab. So 3 chi3 over 4. It has a 4 here. This 4. 4. 1 plus chi1. Okay? And an alternative way of writing the intensity dependent refractive index is by means of the equation. So we could write this, the equation for the refractive index, in terms of the intensity of your laser. And we could like see that this intensity will be proportional to E square, this E square here, the amplitude of the field. So let's check this. So to find E and N2, and that's why I put here N2, the bar, because they are not the same, they will like change. Remember that the intensity I could be written as a velocity of the, in this case, or your wave times the time averaged energy density. So U is the time averaged energy density. And in the medium, the velocity, because we are considering like light, so in vacuum, V is equal to C0, if you want. It's the velocity of light in the vacuum. Velocity of light in vacuum. But in the medium, in a medium, this velocity is the C0 over eta 0. So this is the velocity of light in the medium, called V. And to evaluate this, we remember for classical electrodynamic course, like the energy density can be evaluated using like U can be calculated using, it's called like pointing theorem. That in general, it's given like d e plus 1/2 b h. This is the magnetic field. This is the electric field. But because in general, this is much smaller when we are the case we are considered. This term is much smaller than this one. So we could like approximate this to 1 dE. Because in general, B much smaller. And just to remember here, B is μ0 h, the magnetic permittivity, and D epsilon 0 E plus the polarization vector E. Okay? This is epsilon. Questions?
Yeah, Carlos, I seem to be the guy bugging you today, but when I think of optical intensity, I usually think of the classical definition, which is energy per unit area,
Yeah, this here, right?
right? How does that compare to you? Is it equivalent to your definition?
Yeah, because this is the energy density.
The energy density is what contains that. Okay, great. Thank you.
Yeah. So okay, so U, we could like evaluate U in the material, U of T. Just use this here. So this is 1.5. Okay, I need to still write P. P is the polarization factor, so D would be written as epsilon 0 E plus epsilon 0 chi1. We can go only to first order, is enough to what we want to show, because the other terms will be much smaller. We have like a zero order term here, for instance. So this could be written, like, let's say, approximation to this. Epsilon 0, 1 plus I1 E. And this was our definition of eta 0. Okay? This is eta 0 square. So this is epsilon 0, eta 0 square E. Right? And make this multiplication here, this scalar product, we would find like U, the energy density per time. This is averaging time, right? So this is 1.5. That is this 1.5 here. Epsilon 0, eta 0 square, and the average in E. And we already calculate the average in E in the beginning. we know it's proportional to E omega squared. So you could find the intensity here. This definition, like the velocity times the energy density averaged in time. So in the velocity of the light in the medium, C0, eta 0, times this guy here, that's this. So 1, epsilon 0, eta 0 square, E square. So the intensity is this. Epsilon 0 epsilon 0, eta 0, C0 squared. So, okay, so with this, so my eta is eta 0 plus eta 2 times the intensity that we found here. So it's 1.5 epsilon 0 C0 eta 0 E squared. And from equation 1, just to we'll write here again, don't need to see, go back in terms of eta 2 bar E squared. So we could find like that using this in both sides. So eta 0 plus 2 eta 2 bar E squared is equal to this. Eta 0 plus 1.5 epsilon C0 eta 0 and 2 E squared. So this goes with this guy. And we'll find that eta 2 is 4 eta 2 bar epsilon 0 C0 eta 0. And we found above that eta 2 bar is equal 3 pi 3 1 plus chi 1 1.5 square root of this. And make this substitution, eta 2 will be 3. Yeah, because this is so, but we have find that, okay, eta 2 bar is equal to 3 chi 3 4 the square root of 1 plus chi 1. That's the same of writing 3 pi 3 over 4 eta 0, because this is the definition of eta 0. the linear part. So eta 2 will be just 3 chi 3 epsilon 0 c0 eta 0 square. Okay, so we have eta 2. We could like evaluate it in terms of this. All these are measured things. Eta 0 is depends of chi 1, chi 3, the speed of light in the vacuum, epsilon 0, the free permittivity, electric permittivity. So you could like evaluate eta 2. So we could write eta, that's important for us. So to do quantum computation, it is important for us the following expression. So eta, in terms of the intensity, is eta 0 plus eta 2. So this is the equation 719 in the usage one. I tried here just to give a brief idea how this the equation came, but we can see more details if you guys wish in the future. Or if this is just enough, I mean, this is what we really need to follow in like in doing quantum computation. And he gives some examples for values. Values of eta. Example. He put he doped glasses so eta 2 in general, the nonlinear term is proportional in the interval. Centimeters square watts 10 minus 14 centimeters. And the other is semiconductors. Conductors. That eta 2 is in this interval. It's much bigger, right? 10 to the minus 10. Because this term is proportional to the chi's, which in general depends of the wavelength that we're considering. And experimentally, the relevant behavior is that when two beams of light of equal intensity are nearly all propagated through care medium. So in this case, each being will experience an extra phase shift of this type. So I have the exponential of I, index of refraction, the difference of the medium and the vacuum, or in this case the medium, and the when I activate the the linearities, non-linearities, is given this way. We saw this in the last, I think last or two lectures ago. So if you use the expression for eta that we found here, simple eta is eta 0 plus eta 2I minus the linear part, eta 0 L omega C0. So the beams will have this shift, eta 2 I L omega C0. Okay, so in general, what we have, if we have like a K material, and not that the eta 2 depends of chi3. So if we have like K material, chi3, say a slab here, chi3 will have two beams. They will have this difference when they go out in the shift. The 2I L omega C0, where this eta 2 here is the nonlinear term. It's proportional to chi3. Chi3 epsilon 0 C0 1 plus chi1. So if you can like see this effect, if chi3 is too small, that can be considered, so eta 2 is 0, it has no phase difference. But when you can like activate that, we can, your field is strong enough that this could be relevant, so a shift like this would happen. So the idea is to use what we see in the next lecture, to use this procedure to make quantum computation. I was thinking that we could see today, but I think we have more than 1 hour already. Yeah, the next step would be like this effect in applied for quantum computation, but we can see in the next Friday. So I'll leave this whiteboard available, and you guys can review. If you think it's too short review about quantum optics, and this is the size L, this L, the size of this Z. So okay, so I think it's enough for today. We can like the next Friday make application. So far was only the classical part, brief summary, but we can see more details in the next. So okay, questions. You guys can ask questions anytime, Bob. No problem. So it's good because sometimes I don't know if you guys has followed the problem of online lectures is this, because when you are in the classroom you can see like the student's face, but here I can see your guys. So because I can see only the whiteboard, so you can make questions whenever. It's no problem.
Yeah, Carlos, I've got a real basic question about the last thing in the whiteboard. That length for the medium L that you mentioned, what's the
Yes.
scale of that? Like, is that meters, millimeters, millionth of a
Oh
meter?
no, I I think in principle it should be something like microns.
Microns. Okay.
Yes. Yeah, it's very, in general it's small, it's very small.
Which is good for
I mean,
computing.
but not, yeah, but I'm not really sure for quantum computation, but I think so because I make some work, but then I make my research, but in a different line, and we consider like this type of materials in microns was the important for us, but was not applied for quantum computation.
Hmm.
But I think it's possible be like microns, no problem. Micron, I think is 10 to the minus 9, right? Meters.
Um, it's interesting just to comment that this using this change in refractive index to implement a phase shift in the light. Uh, Looking back at that chart, um, I see you have two light sources going in and one coming out.
Yeah,
What
yeah.
happened to the other beam?
Oh, I think they in this case like they just interact, and this interaction will give like this part. We see some examples when we see like the quantum.
All right, so it's
The
not like
quantum,
one's the control and one's the actual beam itself. Okay, gotcha. All right.
yeah, yeah. We see. I was planning like to have the examples today, but I think it's too late. Actually, I'll stop like the recording, and but you guys can make questions even after. Let me just stop recording. So next Friday we see the quantum part for people that are watching YouTube. So okay, so bye.